This week, we're going to move from kinematics of rotation and things of size and shape to kinetics, so why things move. So we're going to start going back to the fundamentals of kinetics that we did in the first part of the semester, really the middle of the semester, and come back to them now with objects with size and shape. So a couple of examples of kinetics equations. Remember Newton's second law, sum of the forces is equal to mass times acceleration. In this case, we need to know information about forces, mass, and acceleration. So we've talked a lot about acceleration in the kinetics part. Forces are going to change a little bit now, and we'll talk about that later. And we'll also need to think about mass. So conservation of energy, kind of similarly, we have the sum of the initial kinetic energies, plus the sum of the potential energies, plus the non-conserved work, goes to the final kinetic energy and the final potential energy. And I want to point out here, again, a lot of these terms have mass. Kinetic energy, 1/2 mv squared. So we have that mass term. Potential energy, one of those is gravitational potential energy, mgh. Again, we have mass. And so we're going to need to be thinking about mass as we transition to rotation. And I've brought a really great example here of why pure mass isn't going to work when we start talking about objects with size and shape. So I've brought a splitting maul. If you've ever split firewood, you've maybe used one of these. It has a very heavy head and a very light and long handle. And you can imagine if I'm trying to rotate this, it matters how I try to rotate it. So for example, if I hold it down here and just try to swing the handle part of it, this is really easy to do. Not a lot of resistance in that rotation. If I flip it around instead and try to rotate it about this end of the handle, this is really hard and it's going to take a lot of work for me to not smash my floor right now. And so it matters not just the total mass, but how that mass is distributed and how we try to rotate objects that have mass. And so the rotational version of mass that we use, we call mass moment of inertia. And we use the letter I to approximate that. And so I'm not going to go into the derivation here. I'd recommend you look at a textbook or somebody else will tell you how to derive this. But the definition of mass moment of inertia that we're going to use is that the mass moment of inertia is the integral of r squared dm for all of the mass. So it matters how far away from the center of rotation that mass is, and we add that up for all the pieces of mass. And this is the r squared and not the r, and I'll show later that that makes the units work out, and really that this is what we want. So this is the definition that we're going to use in this class. If you're freaking out about this integral, don't worry, I'll make it easier. But that is what mass moment of inertia is, and a little bit about why we care about it.